saw. And so the graph there is showing on the vertical axis what we actually measured from the samples, and on the horizontal axis what we calculated based upon the quinones that we measured. And what we find is that, I should take a step back first, the slope of that line will be 1 if we're getting everything perfectly right. If we're measuring everything that's in there that's reacting in the DTT assay, the slope should be 1. If the slope's greater than 1, it means we're missing something. If the slope's less than 1, it means that we're over-predicting how much peroxide is going to be formed. So there are a lot of issues involved in generating this data. So the slope is less than 1, but it's not significantly less than 1. And so what that's telling us is that for the most part, we're accounting for at least the quinones that are reactive in this assay. And then when we look at the quinones that we measure, we find that phenanthroquinone is the one that really dominates the reactivity. So at least within the quinones in this assay, we have this one chemical that's really dominating what's going on. That's not to say that lots of other chemicals are bad for us, but just in this particular case, we have this one chemical that's present in a very, very tiny amount that has a very significant effect. Okay. So then the other question that I posed was, where do these quinones come from? Are they emitted directly from the source, or are they formed in chemical reactions in the atmosphere? And so we've done various measurements over the course of several years. None of them were really designed specifically to answer this question, but we get some insight into what might be going on from the work that we've done. So the first measurements that I'll talk about here were some measurements that we did towards the end of 2005 through mid-2006. And here we were collecting samples with an impactor with different size cuts. And we were doing a very crude version of what Wolfgang does in terms of looking at the chemicals and looking for correlations between the quinones and the PAHs and other compounds that are markers for different pollution sources. And so here's what we saw for the quinones and the PAHs. So on these graphs we have the black bar chart and the red bar chart for the quinones and the PAHs. We have p-values and r-values. So on the horizontal axis we have different sources of particulate matter. And so here, a small p-value and a high r-value means that there's a strong correlation between the pollutants, the quinones, and the source. And vice versa, if the p-value is high and the r-value is low, then there's no strong correlation. So there's nothing that surprising that we see here. The compounds that you've already heard about that generate PAHs and quinones are the ones that are correlated with the samples that we collected. So gasoline, wood combustion, diesel exhaust, these are all things that we know generate these compounds. And so there's no surprise really to see that they're correlated. But what this doesn't really answer for us is whether or not the quinones are emitted into the atmosphere directly from the source, or are they being formed in chemical reactions of the PAHs in the atmosphere and then we're sampling them. And we know that PAH compounds can produce quinones. So here, there's a partial reaction scheme. I, believe it or not, simplified this for you quite a lot. In the top left, we have a 2-ring PAH in the figure there. And then if we go through a series of reactions with these hydroxyl radicals that we've heard about being important in the atmosphere, and go all the way down to the bottom, then there are 2 boxes at the bottom, P3 and P4. Those are 2 quinones that are formed from the PAH. And when people do the measurements, they find that the yields of those quinones are actually very low. They only constitute 1 or 2% of the PAH that's been converted. But because PAHs typically are present in much higher concentrations than quinones, you don't need a big yield in order for the quinone to potentially be the PAH to be potentially a big source of the quinone. So is there any evidence for this photochemistry in the atmosphere? Until 2 or 3 years ago, I'd say no, but there's some work that's again come out of Southern California that strongly suggests that it is an issue, at least in the summertime down there. So this is some work done by John Freund's group at UCLA. And so you can see there's a map here that's of Southern California, and there are these rectangles that are labeled with 3 letters. These are sampling sites that they used during the study. And then there are these sets of black points that represent the trajectories of air masses moving across Southern California over the course of a day. And so what this group did is they collected samples from those sampling locations, and they looked for the concentrations of phenanthrene, phenanthroquinone, and this benzopyrrolene, which they used as a marker. And from those measurements, they can see the quinones being formed as the air moves across Southern California. And by the time it gets to Riverside, which is that last point on the right-hand side, it constitutes something like 90% of the quinone that they see comes from the chemistry, not from direct emissions. But of course, as we've heard already, the air here is not the same as the air in Southern California. This is just some monthly averages for PM 2.5 mass loadings over the course of 2009 in the San Joaquin Valley and here in the San Joaquin Valley and also in LA. And you can see just by looking at it, there are differences there. So of course we know now that PM mass loadings tend to be much higher in the winter than in the summer. In Los Angeles, there's much less variation, but there does tend to be a bit more PM 2.5 in the summer, presumably due to photochemical reactions that go on, and then the chemicals deposit into the particles and increase the mass. But of course, there are times here when we do have high levels of PM, when we have wildfires. So this satellite image on the left is from, I think it was July 11th of 2008. And the red dots on there are all individual fires, and you can see the smoke plumes coming off of those. And there's a plume coming directly down from Northern California right into the San Joaquin Valley. And when we correlate that with the PM 2.5 masses, we see higher levels on those days. So July 11th, in that graph at the bottom there, the black bar chart corresponds to a high day for PM 2.5. So we were able to get some filters from the Air District and do a little bit of chemical analysis on those for this period. We only have 1 in 6 day samples, which is what they collected. We can see levoglucosan is elevated on those days when we have these smoke episodes, just as we'd expect based upon it being a tracer for wood smoke. When we look at phenanthrene, for that first period, that first high PM period in June, we don't see any elevation in phenanthrene in that first period, but we do in the second period. But we don't see any phenanthroquinone at all in this entire period. And it could be that it's not being formed in chemical reactions, but it could also be that it's really hot at that time of year, and so we expect these things to be driven into the gas phase. So we didn't have the semi-volatile data to compare that to, but we don't see evidence of the photochemistry here. But if we go to some older data that we collected from 2004, where we're looking at a bigger quinone, this is a 4-ring as opposed to a 3-ring, then we potentially see some evidence for maybe some photochemistry. So if we look at the green bars here, this is for naphthene quinone, collected over a 24-hour period on different days during the summer. Some days we have really high levels of this compound, and some days it's really low. And when we were looking at differences between those two sets of data, the only difference we could really find was in the air mass trajectory. When the levels are low, the air mass had avoided the Bay Area prior to arriving in Fresno. On the high days, it had gone right over the Bay Area. And so these are days when we expect to see photochemistry going on, and we don't have the resolution of the data to say it's coming from photochemistry, but it may be coming from photochemistry. Something else that hasn't really been touched upon yet is the relative role of nighttime versus daytime chemistry. So most of the chemistry in the atmosphere that we talk about is driven by sunlight. A lot of it's driven by hydroxyl radicals and ozone, but of course at nighttime those things aren't around, but you do tend to get a buildup of this NO3 radical, and that can also initiate chemistry as well. So about 3 years ago, the ARI group at UC Riverside did some laboratory measurements to see, for these 3 oxidants, hydroxyl radicals, ozone, and NO3, which of these can generate phenanthroquinone, a quinone from a polyaromatic hydrocarbon, phenanthrene. And so if you look in the table, the first line in there are the yields that they measured, the experimental yields that they measured in the laboratory for the reaction of those 3 reactants with phenanthrene, and you can see that the reaction with NO3 generates far more phenanthroquinone than the OH and the ozone. But of course, that's not the whole story. These different chemicals react at different rates with the phenanthrene as well, but also the concentrations of these things in the atmosphere are different. So you need to take all of those things into account in terms of predicting which is going to be the most important for producing this particular quinone. In this case, when they went through the analysis, they are predicting that the NO3-initiated chemistry actually produces far more of the phenanthroquinone from phenanthrene than the other pollutants. So because of that, we decided to try and do some daytime, nighttime measurements here in Fresno. So we had 2 sampling sites, one on our campus and the other one close to downtown Fresno, not too far from here. And we collected over about a 2.5-week period. At Fresno State, we had daytime samples and nighttime samples. At the downtown site, it was just during the day. And so I'm showing you on the left some data for chrysene quinone. And so the blue and the red